So hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello and welcome tonight. So we're exploring how RAG systems enhance LLMs using vector databases and HNSW. Discover how this algorithm speeds up information retrieval with close enough searches, improving semantic search, despite some kind of memory trade-offs. Can you explain how Retrieval-Augmented Generation RAG systems leverage vector databases to enhance the performance of large language models, LLMs, so when retrieving relevant information?
Retrieval-Augmented Generation RAG systems work like a super smart librarian who can really quickly find the right books from a huge library. In this case, the library is a vector database which stores information in a way that makes it easy to find so. Imagine you have a giant library filled with so many books, but instead of titles, each book has a unique code that represents its content. When you ask the librarian a question, they don't read every book. Instead, they use a special tool like a magical map to quickly look up which books are most relevant to your question. So this magical map is similar to what we call an embedding model, which turns text into a pretty dense vector. Now the librarian uses a method called nearest neighbors, chobayan, search to find the closest matches to your question. This is like finding the books that are most similar to what you're looking for. However, if the library is really, really big, it would take a long time to check every book. So the librarian uses a smart shortcut called the Hierarchical Navigable Small World algorithm. This algorithm helps the librarian find good enough answers quickly, even if they aren't so perfect matches. In summary, RAG systems enhance large language models, LLMs, by using vector databases in the HNSW algorithm to quickly retrieve relevant information, making it easier for the AI to actually give you the answers you actually need.
What specific advantages does the Hierarchical Navigable Small World HNSW algorithm provide over traditional nearest neighbors, TAME methods in the context of vector databases, particularly regarding speed and efficiency in handling large datasets?
The Hierarchical Navigable Small World HNSW algorithm brings some pretty exciting advantages over traditional nearest neighbors, especially when dealing with large datasets. Think of HNSW as a multi-layered cake, where each layer helps you find what you're looking for more quickly. Like the bottom layer contains all the documents, just like the base of the cake, just holds everything together. This layer is pretty similar to the traditional Kani, where you would check every document to find the closest matches. However, HNSW adds extra layers above this base, creating shortcuts that make searching faster and more efficient. So when you want to find a document, HNSW allows you to start at the top layer and quickly navigate down through the layers. So this is like taking an elevator to the top of a building and then using stairs to quickly get to the right floor without having to walk through every room. This hierarchical structure speeds up the search process because it reduces the number of comparisons needed to find the best matches. So in summary, HNSW improves upon traditional CAN methods by using a layered approach that speeds up searches and makes it more efficient to handle large data sets. So this means that even when there are millions of documents, HNSW can help find relevant information so much faster.
Could you elaborate on the logarithmic time complexity of the HNSW algorithm and how this characteristic influences its performance compared to other approximate nearest neighbor search algorithms?
The logarithmic time complexity of the HNSW algorithm is like having a super efficient treasure map that helps you find the treasure in a huge field. So when you have a large data set, say millions of documents, the way you search for information can make a really big difference in how fast you find what you need. In this case, the logarithmic time complexity means that as the size of the data set increases, the time it takes to find the nearest neighbors grows much more slowly compared to other methods like traditional nearest neighbors. So CAN obviously, which has a linear time complexity. Imagine if you had to check every single room in a giant mansion to find like a hidden treasure. That would take a long time, but with HNSW, you can quickly narrow down your search by skipping so many rooms, thanks to its layered structure. So if you think about it, obviously with HNSW, if you double the number of documents, the increase in search time is pretty small, while with CAN, doubling the number of documents would mean you might have to check twice as many rooms. This characteristic allows Huntstar to perform so much better in practice when looking for information in large datasets, making it a popular choice for vector databases used in RAG systems.
So what are the trade-offs involved in the higher computational cost associated with the graph creation and updates in HNSW? And how do these trade-offs impact its practical application in RAG systems, sort of?
The higher computational cost associated with creating and updating the graph in HNSW comes with some sort of trade-offs. Think of it like building a really complex amusement park. While the ride's graph structure can provide thrilling experiences, fast searches, constructing and maintaining them requires a lot of resources, time, memory, and effort. One trade-off is that HNSW requires more memory to store the graph structure and the vector embeddings. So this is like needing a larger area to house all the rides and attractions in the amusement park. So if your system has limited memory, it may struggle to keep up with the demands of storing all this information, which can slow down performance. Like another trade-off is basically the computational cost involved in updating the graph when new documents are added. Just like adding a new ride to an amusement park requires planning and construction time. So updating the HNSW graph can take time and resources. This means that while searching can be very fast, once the graph is built, keeping it up to date can actually be a bit of a challenge in practical applications within RAG systems. So these trade-offs mean that while HNSW can provide quick and efficient searches in large datasets, it may also require careful management of resources and planning for updates. So if the system can handle the memory and computational demands, HNSW can be a really powerful tool for retrieving relevant information effectively. However, if resources are limited, it might be necessary to consider simpler alternatives or optimize the use of HNSW to balance performance with resource usage, like.
How does the multi-layered graph structure of HNSW facilitate close enough semantic searches? And why is this level of approximation so beneficial for RAG systems that utilize large language models?
The multi-layered graph structure of HNSW helps facilitate close enough semantic searches by organizing documents in a way that makes it easier to find relevant information pretty quickly. So imagine a multi-story library where each floor has a different category of books. When you search for a topic, you can start on the top floor and really quickly narrow down your options as you move to lower floors, each containing more specific information. So in HNSW, the highest layers have fewer documents, allowing for faster navigation to find nearby matches. As you go down each layer, you get closer to the specific documents that relate to your query. So this layered approach means that even if the algorithm doesn't find the exact match, it can still return documents that are very similar or close enough to what you're really looking for. So this level of approximation is really beneficial for RAG systems that utilize large language models, LLMs, because it allows for quick retrieval of relevant information without needing to find the perfect match every time. So in many cases, having a document that is similar in meaning is just as useful as having the exact document. Like, this speeds up the process of providing answers and enhances the overall performance of the system, making it more efficient for users who need timely information. So in summary, the multi-layered structure of HNSW enables effective close enough searches, which is particularly advantageous in RAG systems, allowing them to provide relevant information pretty quickly and efficiently.
Can you discuss the implications of using HNSW as the default algorithm in popular vector databases for the broader field of information retrieval and natural language processing?
Using HNSW as the default algorithm in popular vector databases has significant implications for the broader fields of information like retrieval and natural language processing, NLP. First, because HNSW is designed to efficiently find close enough matches, so it enhances the performance of semantic searches. This means that when users search for information, they're more likely to receive relevant results pretty quickly, even if the exact match isn't found. This capability is crucial in NLP applications where understanding the meaning behind words and phrases is essential. As a result, users can expect a more intuitive and effective interaction with AI systems, so leading to better user experiences. Second, since HNSW requires more memory to store its graph structure and vector embeddings, it encourages developers and researchers to think critically about resource management when building information like retrieval systems. So this can lead to innovations in how data is stored and accessed, as well as improvements in hardware and infrastructure designed to support these algorithms. Furthermore, the widespread adoption of control in popular vector databases means that it sets a really standard for performance in the field. As more systems implement this algorithm, it can actually drive advancements in related technologies, pushing the envelope on what is possible in information retrieval and NLP. In summary, so the use of HNSW as the default algorithm in vector databases promotes faster and more relevant search results, encourages thoughtful resource management, and sets a benchmark for performance, all of which contribute so positively to the evolution of information retrieval and natural language processing.
So thank you for joining us today for this insightful discussion. We've explored how retrieval-augmented generation systems are so dramatically enhancing large language models. At the core of this advancement lies the sort of crucial ability to efficiently retrieve relevant information, a task brilliantly handled by vector databases, leveraging algorithms like Hierarchical Navigable Small World or HNSW. We just learned that HNSW offers significant advantages over traditional nearest neighbors by employing a sophisticated multi-layered graph structure. So this innovative design allows for searches with logarithmic time complexity, meaning that as datasets expand, the time needed to pinpoint relevant documents remains remarkably efficient. Of course, this efficiency really comes with its own considerations. So we discussed that HNSW does require higher memory allocations and increased computational effort for updating its intricate graph. Yet the close enough searches it facilitates are proving so incredibly beneficial for RAG systems, enabling quicker access to semantically relevant information without needing exact matches. The widespread adoption of HNSW as a standard in vector databases is truly transforming semantic search performance, encouraging better resource management, and just setting a new benchmark for advancements across information like retrieval and natural language processing. It's really clear that this technology is a foundational element in the evolution of AI. A big thank you to our researcher for sharing such profound insights into this sort of complex yet vital area. And to you, our audience, thank you for tuning in. So we look forward to having you with us again for our next exploration into the cutting edge of technology.